Okay, so we're going to pick up here with our discussion about this reaction, which I mentioned was a propane reaction. We're not actually burning a puppy. That would be horrible. Okay, so this molecule is a representation of propane, where the black ones again are carbon. The white ones are hydrogen. All right, and so it has 3 carbons and 8 hydrogen in this one particle, this molecule. Okay, so we can think about it as one molecule of propane, and it has to react with a total of 5 molecules of oxygen. So 5 individual pieces of oxygen have to react. Oxygen is diatomic. It's always present as O2. It's never going to just be O. So that means that while we have 5 molecules, I actually have 10 atoms. So it's just the subscript times the coefficient here. So 2 times 5. And that's where we get the number 10. Okay, so 10 atoms. You can also just look at the picture and count them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's where the 10 atoms of oxygen comes in. It's important to count our atoms because I should have the same number of oxygen in the beginning that I have at the end. Otherwise, the reaction isn't what we call balanced. Okay. So we get to learn more about that in this chapter. Now, our products of a combustion reaction, as we learned, for one thing, before we get to products, we have to have oxygen as a reactant. It's required. You must have oxygen to burn anything. Otherwise, it's not combustion. Okay, so we have our fuel and our oxygen. Okay, and it's going to produce carbon dioxide and water. Now, these numbers in front, these are called the coefficient. Okay, just to review that. And what it means is I have 3 of the entire particle, so 3 carbon dioxide molecules is what we produce here. That means there's 3 atoms of carbon because 3 times 1 is 3. And there must be 6 oxygens because it's 3 times 2. Okay, and so you can count the red spheres, that's your 6. It also is going to make 4 molecules of water. So 4 oxygens are here and 6 oxygens are here. So they're going to add up to the total number of oxygens that we start with. 4 plus 6 equals 10. All right, so that's an important idea. We also have the same number of carbon atoms on both sides and even the same number of hydrogen atoms on both sides. We're going to learn about this quantity, the mole. The mole is kind of sort of a synonym for molecule. It's just a unit that we use to symbolize the same concept of if one molecule reacting with 5 of these. We could say 1 mole reacts with 5 moles of oxygen, like that. And then another term we get to learn about is something that we call molecular weight, or sometimes formula weight, molar mass is another term. All of these terms basically mean the same thing. What they mean is we look at the formula here and we look at the periodic table. So for carbon, the periodic table says that carbon is 12.01. Hydrogen is 1.01. So to get this 44, what they do is take the number of carbons and multiply by the weight of each carbon, and then add 8 hydrogen, which each weigh 1.01. So it would look like this. So we have 12.01 for each carbon, and there's 3 of them. And then we have 1.01 for each hydrogen, and there's 8. So we're going to add this total all together, and you get 44.09. So if I weighed out 44.09 grams of propane, it would react with precisely 160 grams of oxygen, because we said there's 5 molecules. Each molecule has 2 oxygen in it. So when I look at the periodic table, oxygen is listed at 16.00, and I got 2 of them, so that's where this 32 comes from. And I multiplied by 5 because we said that there's 5 total oxygen. So I'd have to react 160 grams of oxygen with 44 grams of propane. It's going to produce 3 carbon dioxide, which a single carbon dioxide weighs 44.01 grams. And then our water, there's going to be 4 of them, and it weighs 18.02. So what's interesting is if I take 160 grams on the left and I add up the 44, we get about 204 on that side. On the other hand, if I take the number of carbon dioxides and I add it up with the mass of the water. I'm rounding a little bit just to make the mass simpler, but we still get 204. This is the law of conservation of mass. It says if I add up everything in the beginning, it's going to add up to the same thing at the end. In order for this to be true, we have to know these coefficients correctly. We have to know that there's 3 carbon dioxides for every propane. Okay, that kind of information is really valuable. And that's only something we can get out of a balanced reaction. So that's pretty much the focus for the rest of this chapter, those ideas. All right, so molecular weight is from the periodic table. So the first thing we need to get is our periodic tables out. Okay, I've got mine, so I'm assuming you're going to be using the same green one that I gave you in class, that we were all talking about the same numbers. All right, so for like sulfuric acid here, H2SO4, it has 2 hydrogen, because there's a subscript right here, so I'm going to say 2, and the weight of 1 hydrogen is listed on here, 1.00794. I normally just keep 2 decimal places because it's convenient, so I'm going to do that. The unit that we're going to use the most often when we pull it off the periodic table is grams per mole, so I'm going to write that. So that's my 2 hydrogen. Then I got a sulfur. A sulfur is element number 16, so it says 32.065. I only have 1 of them, so I don't need to multiply that sulfur by anything. It's just 1 of them. So, and then there's 4 oxygen. Each oxygen, it says 15.9994. I'm going to round that to 2 decimals just because it's convenient. Okay? I usually don't need more than 4 significant digits, so if 2 decimals is 4 digits, so that's close enough. Okay, so if we add all of these things together, okay, my calculator says the answer is 98.085, which since I have 2 decimals everywhere else, I'm just going to round that. It came up with the 85 from the sulfur here, but and the unit for that is going to be grams per mole. We're going to learn more about moles in a second. For now, we're just going to use it as a unit. All right, so I want you to do these 2. They are graded. So once again, pause the video and try to do these calculations so I can check them out when you turn them in class. Okay, so when we were looking at that picture of the propane, we could visualize single molecules, like 1 propane reacting with 5 oxygens, and that's relatively straightforward. And we can even see that 10 atoms of oxygen are present in those 5 molecules of oxygen. Okay. The problem is that I can't actually count a single molecule of propane. It's impossible. Molecules are so small. There's no way for me to find just 1 molecule of anything. So, if, for example, I want to make water, the process to do that requires 2 molecules of H2. It's a diatomic gas, so that's why it's H2. That's hydrogen. And then oxygen is still diatomic. And these are going to come together to actually make 2 water molecules. Okay? So our total number of oxygen is 2 here and 2 here, because this coefficient applies to the oxygen as well. And then we have a total of 4 hydrogens, so that's 2 times 2 is 4. So that's how I know it has to be 2 water being formed. Now, I can't measure out just 2 hydrogen. I can't do that. I could measure 2 grams of hydrogen. I could measure 2 liters of hydrogen. I could measure any of those physical quantities, but I can't count molecules. It's too small. So instead of counting molecules, we invented a unit whose function is to relate mass, which is easy to measure in the lab, with number of molecules, and we call this unit a mole. And before you ask, no, I have no idea why we settled on that word. It has nothing to do with rodents. It's just what is used. I don't know why. If anyone figures out why, let me know. I'm sure it's a great story. Probably some alcohol involved in that decision, I think, but I have no proof. So, just a little note about the difference between measuring mass and counting molecules. Okay, so like in our classroom, depending on the day, we vary anywhere between 12 and 16 people, right? We know for certain on any given day how many people are in that room. We don't have partial people, so we would not ever have a conclusion that we had like 12.3 people. It doesn't make any sense, right? That means that counting the number of people in a room is a counted value. So that has effectively an unlimited number of sig figs. We know it's exactly 12 people, so you can put as many significant digits as you want. Doesn't matter. In other words, counted numbers never limit our significant figures. On the other hand, if I weighed all of us on any given day, it's going to be different from 1 minute to the next because it's a measurement. And measurements always have uncertainty. Okay, so in other words, that's the idea that the last digit is going to fluctuate no matter what I do. That's part of taking measurements. That's always there. So when we weigh something, the number of significant figures comes from the scale. So in our case, our balance in the lab, the ones in the laboratory, could weigh out to 2 decimal places, which is probably 3 significant figures. The ones in the instrument room, which are called analytical balances, those ones have 4 decimal places. So conceivably, you could get like 5 significant figures from that. Okay, they both weigh grams. So the number of significant figures depends on the instrument that you use to measure it. The balances in the room usually only get about 3. The balances in the instrument room, we can get about 4 or 5. All right. Now the difference between these two situations is that measurements directly impact sig figs. Okay, whereas counted values don't. Okay, and that's an important thing to remember. So if I could count, say, 500 atoms of hydrogen and react them with, 250 atoms, well, molecules actually, of oxygen, then I know for certain how many molecules there are. That would have an infinite number of significant figures. However, since I can't count individual molecules, I have to use a measurement instead. All right, so this is a mole. All right, our definition of a mole is that it contains this many items, 6.022 times 10 to the 23 items. It's kind of like the way that we use the word dozen, right? So dozen means 12 eggs. So when I say a mole, it means I have 6.022 times 10 to the 23 items. So like if I have a mole of eggs, it would be 6.022 times 10 to the 23 eggs. That's more eggs than there have probably ever been on our planet, even if you count things other than chicken eggs. That is a lot of eggs. Okay. So moles are used to describe things that are really, really, really tiny because we have a lot of really, really tiny things. All right, so it's a good unit for that. It's based on the fact that if we had a sample of pure carbon-12, it would weigh exactly 12 grams. Everything is compared to carbon-12 in the modern periodic table. It does get updated as we go along. Sometimes we find the values of the average value of the weight of things change over time as we discover new isotopes and so forth. So this does get updated periodically. Avogadro's number is the symbol for a mole, and it's defined as that many of whatever item you have. Sometimes it's atoms, if I'm talking about individual atoms. Sometimes it's molecules or particles. You can have a mole of anything. It's not restricted to just talking about chemicals. It's just used there more frequently because atoms are small. So each one of these things represents 1 mole of substance. Here is sodium chloride. This is table salt. It has 58.5 grams in this petri dish. So petri dishes aren't very big. It doesn't take very much to get a mole of sodium chloride. It's a relatively small compound. Okay, so we can even think of this as grams per mole. We weighed out 1 mole by weighing 58.5 grams. This comes from the fact that Na is 22.99 and Cl is 35.45. So if I add up the 2 weights from the periodic table, the formula weight is 58.5. So that's how much it takes to weigh out 1 mole of salt. This is iron 3 chloride. It says it takes 270 grams per mole. This is bigger because iron 3 chloride is a bigger compound, FeCl3. iron is heavy and there's 3 chlorine as opposed to just the 1, so we're going to have to weigh out more weight, more mass, in order to get the same number of particles. Since these are both 1 mole, they have exactly 6.022 times 10 to the 23 particles. But our particles are different sizes, so it makes sense that this would be bigger. It's a bigger particle, so you have a bigger pile. So on and on. These are just different substances. All of them are 1 mole. I'm going to show you a fun video to help you remember what a mole is when we go to class. So if I forget, remind me to do that. It's a fantastic video. You're going to love it. All right. So if we try to weigh a single atom, the number would be so small, it's impossible. We don't have any scales that can do that. We can't weigh single atoms. We have to weigh many of them together. So that's where the mole comes in, right? So our definition of a mole is it's just a unit where we can convert between like small things, atoms and molecules, into mass, okay? Right, so when we say molar mass, what that means is those numbers off the periodic table where the unit is grams per mole. So from that problem we just did a few minutes ago, if you look at the mass of silver on the periodic table, okay, it says it is 107.868 grams per mole. Chlorine says 35.453. Okay, so whenever we're pulling these weights off the periodic table, the unit is grams per mole. That literally means to get 1 mole of chlorine, so you can think this is 1 mole, for every 1 mole of chlorine I get 35.453 grams. Okay, so the answer to that is that the periodic table has all the things we need. So our calculated values from before, this was 98.09 grams per mole. If you calculated AgCl correctly, it's kind of based on the one that we just put on the last page. And again, I don't care how many decimal places you keep, but this is what you get if you use all of the numbers on the periodic table that we have. Okay, so these are the answers to those questions I'm going to grade. So if you didn't get those, you need to go back and figure out why you didn't, and show me all that work. Don't erase anything. I want to see how you're thinking so I can help you learn. So these are the values in grams per mole for these 3 compounds. All right, and what it means is if I wanted, this is glucose. It's the simplest sugar in the human body. All right, so glucose has a weight of 180.18 grams. So if I needed to have 6.022 times 10 to the 23rd molecules of glucose, I would weigh out 180 grams of it. Okay, so when we were talking before about way back, when we were talking about how you find the weight of a particular element, it's protons plus neutrons. That has the unit AMU, atomic mass units. When we're talking about molar mass, the difference is it's the same numbers. We're just using a different unit, grams per mole. And that's actually the one that is the most common. All right, so as it turns out, we can go between moles and molecules as long as we remember a couple of things. First off, we need to write down what we know from the problem. We know that there's 1.0 moles of H2. Before we proceed, I just want to point out that the abbreviation for mole is not really much of an abbreviation. Do not use little m. This has different meaning. For one thing, it means mass. We've used that several times already. It's also going to mean something else in the next section of this class called molality, which is not related really at all, so we don't want to confuse little m. These symbols are taken, so instead we abbreviate mole as MOL. I know, it's not really much of a time saver to skip the E, but that's how it is. Okay, don't write little m. I will be very confused. Don't write big M either. Big M has a different meaning also. Okay. All right, so we know that we have 1.0 moles of H2. That's one thing that we know. We also know that a mole, let's say molecules here, because I chose that since H2 is a molecule. It's not an atom by itself, it's a molecule. So it has that many molecules in 1 mole, so we also know that. Okay, so what I need is to use these 2 pieces of information together. as it turns out, this relationship between molecules and moles can be turned into a conversion factor. This is that fraction where one of the units I've got or I want to get rid of is on the bottom and the other one is on the top. So I can take this equality statement, for every mole it's this many particles, and I can turn it into a fraction. So what we're going to do is we're starting out with the information that we know. There's 1 mole of H2, and I'm going to use this fraction, and in this case I want to keep molecules on top because I can put moles on the bottom and cancel it. This is going to tell us how many molecules of H2 are there, and of course 1 times that number is just going to be this number. Okay, so there's the answer. We can use Avogadro's number as a conversion factor. I put moles on the bottom because I wanted to get rid of it, and that's what I started with. You'll note that I did not flip this 1 mole because it's not a fraction. I can't flip it. The only one I can flip is the ones that are fractions. If I did 1 divided by 1 mole, we're going to get a very, very different answer. A very, very wrong answer. Okay, so that doesn't make any sense. And also remember that when you've calculated the number of molecules, it's always going to be a very large number. So if scientific notation is still kind of hazy for you, I really recommend checking out the mathematic review at the end of the textbook. There's a little appendix that's very helpful. I also have an additional supplementary text in my office. You can come and work on that workbook, which is helpful to people. Okay, so using a similar idea here, I want you to tell me how many moles are in, how many molecules are in a half of a mole of oxygen. All right, so show your work and circle the correct answer over here. And this is, of course, graded. All right, so then if I want to know how many atoms of oxygen are in a molecule or a certain amount of moles, we have to do 2 different steps. So I can go from moles to molecules. This is using Avogadro's number like we just saw. And then if I want to go and know the total number of atoms in a compound, I need to use like the subscript. Okay, so each arrow represents a conversion. That means dimensional analysis is required. And the thing written over the arrow is our factor, our conversion factor here. All right, so our conversion factor for oxygen is if I have 1 molecule of glucose. I'm just going to write the chemical name here. So I have 1 molecule of glucose for every 6 atoms of oxygen. And I can either write it 1 molecule for every 6, or equally valid is to say that I have 6 atoms of oxygen for every 1 molecule. I can write it either way, and that's what a conversion factor is. Okay, it's a relationship. I have this many for that many. All right, and so that means I can flip it around however I need to use it. So let's say I have 1 mole of glucose, and I want to know how many total atoms of oxygen are there. The first thing I got to do is convert from moles into molecules. So that's where we're going to use that Avogadro's number. And then the second step is to go from molecules to atoms. Well, I want to get to how many oxygen atoms there are, so I want to put molecules on the bottom here. I'm going to pick that conversion factor that's on the right. And this way, molecules is going to cancel. Molecules cancels, moles canceled here, so we're left with only the unit atoms of oxygen. Now, how you enter this number into your calculator is critical, so you need to practice with this way before your final. Don't wait until you get to your final. I can't help you use your calculator during your test. You have to know this. When you enter scientific notation in a calculator, you can't use multiplication. It's not multiplied by 10. Okay, it's going to do the math wrong if that's what you do. So what we need to use is different buttons depending on your calculator. Some of them say EE, and then you put in 23. Some of them say just one E. Some of them say EXP. There's even some that have 10 raised to a caret. Caret means superscript. All right, and so usually you just push whatever button your calculator requires and enter the number that comes after the times 10. So essentially all of these things, they mean times 10 raised to something. Okay, so practice this with your calculator. All right, if you enter this correctly and then multiply by 6, the correct answer here is going to be 3.61 times 10 to the 24. Now my calculator doesn't say times 10 to the 24. What it says is this. This is from my model. I have a TI-89. This is probably older than most of you, so it's not the most updated one, but this is what it looks like when I get a number. There's more digits. I didn't write all of them, but this e to the 24, that's my exponent. E means exponent, right? When we write things down on our tests and so forth, we want to use correct scientific notation. We don't write like computers because we're not computers, but I have to be able to interpret what the calculator is telling me. Again, these numbers are so big that we have to be comfortable using scientific notation. So if that's something that you're struggling with, then be sure you practice. Okay, so we can go backwards. And the conversion factors are going to be basically the same thing, just flipped over. So to go from molecules to moles, I'm going to use the inverse of this one, and I'm going to use the subscript but flipped because I'm going backwards this time. I'm sorry for the ringing. That was my office phone, which I cannot mute. All right, so anyway, I want to start with my given information here. That's what I have, so I'm going to start there. And I keep the unit and identity. So atoms of oxygen, I'll shorten oxygen just to O. All right, and so we can figure out how many moles of H2O were there to begin with by using this method. So I have atoms of oxygen here. That means I'm going to first use the subscript. I'm going to put atoms on the bottom because I'm trying to cancel it. And it turns out in water there's only one atom of oxygen, and that's for every one molecule of H2O. Okay, and then the next step is Avogadro's number. Wow, that's crooked. We're going to use Avogadro's number, except I want to get 2 moles. So in this case, we're going to put moles on top. It's still 1 mole, all right, and we still have this many particles for that 1 mole. In this case, our particle is molecules of H2O. Okay, now this is the part where if you don't enter it correctly, the calculator is going to calculate it incorrectly. Okay, so first I put 5.93. EE is what my calculator says. It might be different on yours. And then I entered 25, and so that's the starting information. Multiplying by 1, I don't need to put it in my calculator because I know that that's not going to change the numerical value. All we're doing by multiplying here is changing the units. So atoms are going to cancel. And then in the next step, I'm dividing by molecules of water. So molecule and molecule are going to cancel. And that gets us the unit the question is asking for. I always like to do a double check, like moles and moles. Okay, so those match. All right, so back to the calculator. So it's 5.93 e to the 25. So I just write E25. And then divided by, because our Avogadro's number is on the bottom there, 6.022 EE23. And so if we did that correctly, the answer will be 98.5. Well, it says 98.4723, but I'm just going to round because I had 3 significant digits in the beginning. And this would be moles. So that's a whole lot of water. 98 moles is a lot of water. Okay. If I don't enter this digit correctly, I get some funny values. So if you get anything besides what I've shown you here, then you need to come see me ASAP so we can work out how your calculator works. All right, so now to connect the dots to what we already learned in the earlier part of this chapter, molar mass. since that has units of moles, it can be used to go between mass and moles, or even moles and mass, right? So here's an example. Actually, let's do the water one from a second ago. We just said there's 98.5 moles of water. So if I want to figure out how many grams that is, because I don't picture really like moles very well in my brain, but grams makes a little more sense. All I got to do is find the molecular weight, or molar mass, it's the same thing, of water. And so 2 hydrogens and also 1 oxygen. So we get 18.02 grams per mole. So this is a conversion factor. We could even think of this, if it helps, as a full fraction, like grams on top, moles on the bottom. In fact, this is a much better way of writing it than doing it like this. We do this for computers because typing is easier if you use a slash instead of the fraction bar. But this is really difficult to interpret mathematically, so don't do that. And if you are doing that, break the habit now. Trust me, it'll save you heartache later. Okay, so we have calculated our molecular weight right here, and I get to use it because it's dimensional analysis. It's just multiplying by a fraction. All right, and I put moles on the bottom because I want it to go away. So what I'm going to actually enter is 98.5 times 18.02. And it says 1,700, wow, that's a big number. Okay, 1,774. That's too many significant figures. I canceled everything but grams, so we're going to keep that. So the numbers I get to keep is 3 of them. There we go. You'll notice I rounded. I didn't just drop the 4. That would be 177, which is different than 1,770, right? Just ask yourself, would you rather get $177 or 1,770? Okay, so that's how we would go from moles to grams. To go in the opposite direction, I'm going to clear up some space here. Hopefully you don't write as big as I do, but to go the other direction, so from like 4.5 grams of something into moles, it's the same process. We do need to know what ammonium chloride is. So ammonium is on the back of the periodic table, and it says NH4+. And so chlorine is just Cl, and the periodic table says it has a -1. So I need one of each of these things to make a compound. So ammonium chloride is NH4Cl. Okay, so to figure the molecular weight, I have to go the weight of a nitrogen plus 4 hydrogens plus the chlorine. So for each hydrogen is 1.01, so that's that, and then chlorine is 35.45. Again, all of these numbers come from the periodic table. So our final mass here of ammonium chloride is 53.5 grams per mole. Okay, so I can use that here. In this case, that's very artistic looking, but not quite what I meant to do. I'm going to erase this out of my way too. Okay, so what we have to do is take that relationship, the fact that there's 1 mole for 53.5 grams, and I got to cancel grams because that's what I'm starting with. So that means it goes on the bottom with that 53.5. They're married. We can't separate them. All right, the stuff on the top is just being flipped to the bottom, and the stuff on the bottom is going to become the top. This means that grams are on opposite sides, so I get to cancel them. What I'm going to enter in my calculator is 4.5 divided by 53.5 because this number here is on the bottom. I don't care about the 1 because it doesn't change anything mathematically. Okay, so I chose to cut off my significant figures at 2 because I have these 2. So these zeros don't count because they're in the front of the numbers. But the 8 and the 4 count, so I'm just going to keep those 2. My calculator gives me a bunch extra that I don't need. But this is how we get to moles from mass. So what we just did is going, this is the ammonium example where we went from mass to moles, and we used molar mass in this one upside down. Okay, so we can even write right on here that moles goes on top and grams goes on the bottom for this one. Okay, and then in a prior example, we went from moles of something into molecules. That uses Avogadro's number, right? So that's, you know, basically this, but flipped over. Well, you can't read that very well, can you? Let's do this. It's tricky when I have to write on colored surfaces. Okay, so if we have moles and we want to get to molecules, this is how we do it. Then if we have molecules and I want to get to atoms, you're going to do the subscript. This is similar to, so from molecules to atoms is similar to what we did here, molecules to atoms. So that's using the atom subscript divided by one molecule. Okay. So this chart is kind of like a map, right? If I'm starting in mass and I want to get all the way to atoms, I have to go through 3 different conversions to do it. Each arrow is a fraction, a conversion. So from mass to moles first, which we use the molar mass for, and then from moles to molecules, Avogadro's number, and then from molecules to atoms, we get the subscript, okay? We could also go the other way, right? We could start at atoms and go forward. But we need to show each conversion separately, and we need to be using dimensional analysis for all of them. So this map kind of helps you to figure out, okay, what's my strategy? Like, say if I'm starting with moles and I'm trying to get to atoms, how many steps do I need to take? Okay, so this is a helpful thing to keep around. Okay, so going back to our balanced chemical reactions, when you have created a balanced reaction by fixing the coefficients in the front of the molecules so that you have the same starting and ending atoms. By doing that, you've created something really, really important called a mole ratio. And the reason a mole ratio is such an important concept is it allows you to relate different substances. Okay? So we have fancy words for this, stoichiometric equivalent quantities, right? Stoichiometric. Stoichiometric just means relating different matters to each other. So in this example, you could relate hydrogen and oxygen, like how much hydrogen do I need to react with a specific amount of oxygen? You could also do the same thing. You could ask yourself, how much water am I going to make? So this is the crux of chemical reactions, predicting how they go, which is chapters 10 and 11 that we already covered, and then using that knowledge to tell how much stuff is made. Okay, that's basically, you know, the main point of Chem 111. As it turns out, I can use these coefficients as equivalence factors. So if, for example, I had 10 moles of H2 and I wanted to know how much water is being made, all I have to do is look at these coefficients, and I put H2 on the bottom because I'm trying to cancel it, right? Trying to get rid of that. And I'm going to put the coefficient for water and the molecule water right there. So as it turns out, I would make 10 moles of H2O. Okay. This thing is a molar ratio, and it comes from the balanced reaction. So here's those numbers. Okay. So we can think about a balanced reaction in many different ways depending on what's convenient. If I want to picture what's happening on an individual level, I would think about molecules. So in this case, we have 2 molecules of H2. That's what the coefficient here means. We also have 1 molecule of O2, and it produces 2 molecules of H2O. You could think about it in terms of moles too. You could react 2 moles of H2, and if you did, you would need 1 mole of oxygen, and you would produce 2 moles of H2O. So those are kind of equivalent statements. That's because moles are just a convenient way of counting molecules without actually having to do it. Okay, so that's where this mole ratio idea comes from. The coefficients are equivalent to the number of molecules. So here's an example from lab. We did this where we added a little bit of heat and we decomposed potassium chlorate. All right, so if I start with 5 moles of KClO3, which is a lot more than we did, by the way, that's a lot of material, I can figure out how much O2 is being made by putting 2 KClO3 on the bottom. That comes from the balanced reaction. This is our mole ratio, so it's from the balanced reaction. And I want to get to oxygen, so I'm going to put the 3O2 on the top. So mathematically, what this boils down to is 5 times 3. That's not a 3. I don't know what that is. Okay, there we go. So it's supposed to say 5 times 3, and then on the bottom we still have divided by 2, and moles is there, and we've canceled KClO3. All right, so this is going to end up being 7.5 moles of O2. That's how much we would make. Now, it's kind of tough to visualize that, so let's see how many grams of oxygen that would be. I want you to do this math. Okay, tell me what the mass of oxygen is. And also, tell me how many grams of KClO3 we used. Okay. So that's it for chapter 9. We're going to go into more depth about that concept of stoichiometry in this next lecture, and then we get to practice it for a couple of weeks because it's such an important concept. It's going to carry us over into being able to tell how much material is made, which is an important thing. It's like if I want to make enough cupcakes for my entire class, I got to know how many eggs to use. So that's kind of the relationships we're going to learn about, and it's all based on that mole ratio idea. Okay, so as usual, your notes will be collected in class and returned with some feedback. So make sure that you go back and do all the things that say graded in this lecture.